here is, let's blow up the sun. I mean, we're not going to explode the sun. But this right here is the center of mass of the sun. And then just a little bit over, right here, is the Barycenter of Sun and Earth system. It turns out, I just looked this up, the Barycenter of Sun Earth is 450 kilometers from center of mass of the sun. 450 kilometers is actually kind of small. And the reason is because the mass of the sun is gigantic compared to the mass of the Earth plus the moon, like by orders and orders of magnitude. So I have so these are kind of like ways to think about using the center of mass. The motion of the center of mass is often the most clear-cut thing to study. And then the motion of the parts of your object or the parts of your system, those things are often more complicated. Yeah. Okay, so I want to move on and suggest another example. And this example is kind of hard to study, but here is a let's explore let's do a semi-mathematical. So let's explore semi-mathematical example. And the example is two masses connected by a spring. So it's going to be a little more technical sounding, more technical than, you know, little comic strip drawings or whatever. So it's a little more technical, and I'm going to use a ruler for that technical adventure. So, so two masses connected by a spring. We're going to use a Hooke's law spring. So, you know, we have a particular kind of spring model in mind. And let me put it like this. So this is going to be interesting. So here is a floor with no friction, right? So, and on top of this floor is an object A and an object B, and they are connected by a spring. And this spring has an equilibrium length. So LEQ is the equilibrium length. And what this means is if A and B are separated, so if the position of A and the position of B have a difference, so I took the absolute value because, you know, if we have an x-axis that grows towards the right, xb is bigger than xa, so the difference is going to be negative. But that negative aspect we don't care about, so I'm just talking about the magnitude of the difference in the locations of A and B. If A and B are separated by a distance that's equal to this equilibrium length, then the force by the spring is going to be 0. If xb minus xa, and just for, it doesn't really matter, but I'll put the absolute value. So if I take the difference in the other direction with the absolute magnitude bars, if these things are separated by a distance that's smaller than the equilibrium length, then the spring force is such, right? So A and B are slightly close to each other. Then the spring has been compressed. So this is a compressed spring, which leads to repulsion. And if instead xb and xa have a separation that is bigger than the equilibrium length, this is a stretched spring, and we have attraction, right? So the two objects, if the spring is too far apart, then the objects are being attracted towards each other via that spring. So this is kind of like a semi-mathematical, slightly technical, right? It's got less thans and equal signs, ways to think about the forces on A and B because of this spring. Okay, so let's say that the mass of B is bigger than the mass of A. So if this is true, then center of mass is closer to B, right? So we are studying the center of mass of B and A together. So let's put A and B in a system, and then the center of mass of A and B, it's closer to the object B. So let's pretend that we know how to calculate the center of mass, or I'll describe how you make a measurement of it. But let's put the center of mass closer to B, like right here. So it's a lot closer to B than it is to A. So this is the center of mass of the A-B system. It's close to B, right? So, good. Then, yeah, so we're being semi-mathematical still and just trying stuff out, right? We're being physicists, really. Okay, so check this out. Here is a boring thing that can happen. A boring thing that can happen is, what if I drew, this is a graph of the position as a function of time versus the time, right? So I'm going to draw this graph, and this graph looks like this. So let's say that the x direction increases towards the right, so the position of B is going to be bigger than the position of A. The x location of B is bigger than the x location of A. So here this is the position in time of object B, and here is the position in time of, say, object A. And for example, down here at t equals to 0, let's say, this would be what would happen if these two things had the equilibrium length between them, so the spring is neither pushing them apart or pulling them in, and they were just gliding constantly at constant speed along this frictionless horizontal floor. Honestly, really boring, right? But this is one of the things that can happen. So we'll say that the distance here is L equilibrium, right? And if you check at a time later, the position of A, whatever it is, and the position of B, whatever it is separate by the equilibrium length, right? So A and B travel along at constant speed, right? They travel along at constant speed with a constant separation. And this constant separation is the separation of A and B just always remaining the equilibrium length apart from each other. But what would be more interesting is if actually these things were oscillating, right, going in and out, sometimes repelling each other, sometimes attracted to each other, just going in and out like this. But they're like traveling sideways while they do that. Can you see this? Like, what if they drifted sideways as they oscillated? And that's what I want to consider. That's the less boring thing to study. So here's the boring thing. The two objects, as they go forwards in time, right, they travel up the x-axis. And so later and later times, they're further and further along the x-axis, but their separation between them is not changing.